Anyway, this is a lot. This is going, well, let's see. Does this work?
Pointing towards those folks
Yeah.
over there. There you go.
Cool. Okay, great. Abstract. A lot of work hacking this into LaTeX. But anyway, so this is going to be a very technical talk. If you want to go to the museum across the street instead, I'll understand. But in any case, let's just move on here. So, right, we're all talking about mathematical modeling, really. Everybody said ML, machine learning, but it's mathematical modeling as far as I'm concerned, right? You want to construct a good model to estimate responses given some observations, right? So what really constitutes an observation and what constitutes a good model? First of all, we should really, nail these things down, right? So I'm going to formalize now. I'm going to write down some math. Sorry. Right, so you've got your model factors or machine learning features or covariates or inputs, right? You have a lot of different terminology for the same things in this space, right? Because in computer science, every 3 years they change the terminology so they can have new hot words, right? A new hot thing. So anyway, hard to keep track. What we really need is a machine learning model to keep track of the names used in machine learning. That would be really useful, I think. But anyway, so right, what are they saying? All I'm saying is that you have a bunch of observations, right? What's an observation? You maybe see the temperature of something, a location, at a certain location at a certain time, or the price of a stock, or the size of a dress, whatever it is. And you have, these observations, you have M of them, each one basically being characterized by n numbers, okay? And then you have your responses or labels or outputs, right, in this response space, which is just some number, right? So maybe you're trying to predict the temperature at a certain location given a lot of information, or the price of a stock given the current state of the market, whatever it is. Okay, so essentially you have this cloud of points that maybe looks like these lights over here, and with some value associated with each one, and then in a particular location, you want to know what the value would be. Right? So what's our model? Our model is then just a function from this n-dimensional space where the factors live that gives you the value. Tries to predict the value, right? And what's a good model? Well, you have this kind of set of models, some space of models that you're going to consider for this problem. And that's the set F, right? Some set of models in the space of all functions. You're not going to consider the space of all functions from Rn to R. It's going to be some restricted set, usually parameterized by some parameters, right? And you're going to try to find the parameters, which we'll get to. So you have this set of models, possible models, and you have some measure of how good the model is, or really how bad it is, let's say, because M is going to measure the error from the model. So a good model is the one that's going to minimize this measure of the error over the set of models that you're interested in, right? Okay, cool. So, for example, statistical model, right? A linear regression. We have this vector in Rn. For a given parameter, vector p, we just are taking essentially the dot product of p with our observations. It gives us a number. Right, that's your model for a linear regression, and then you find the p, which minimizes the essentially the L2 distance. Oh, laser pointer, yeah, this is great. So you're going to minimize the L2 distance between the function values on your observations to the actual values. Right? Okay, great. So what are you doing in machine learning? Well, maybe you're talking about an artificial neural network. Oops, wrong button. How do I go back here? Oh, there's no back. We're stuck. Can you back up a little, one slide for me? Thanks. So, right, so what are you doing with machine learning? Maybe you're selecting the number of levels, the nodes at each level, the activation functions, all this stuff. You get this large space of parameters, so n prime, number of parameters, like the weights, the thresholds, And now given this parameter vector in Rn prime, again, you have some function which basically these parameters give you a model. And you're going to try to minimize the, and again, you have some sort of function telling you how accurate the model is or how big the errors are. And you're going to try to minimize the errors, but with this additional term over here usually, right? Lambda times the length of the parameter vector, okay? So the critical difference here is usually in statistics, you're just fitting directly. In machine learning, you've got this penalization term, the regularization term, right? And why do you have this in machine learning all the time? Usually because you have tons of parameters. You don't have enough data to really set all the parameters. The parameters might also be interacting in odd ways. So you need to do something to try to avoid this overfitting, right? And some people say that, central problem of machine learning is getting your model to work well on outside of your training set. And regularization is what addresses that, adding this penalization. So if you think about it, what are you doing? You're saying, well, think of this p vector, right? This is essentially the sum of the squares of the coordinates. So if you're getting if you have a big value for that coordinate, that's a big coefficient, it's going to penalize the model. That factor, that feature had better be really helping your model to be included, right? That's basically the whole thing. So let's see. So there's a problem though, right? On the other hand, we went through all of this, right? But you'd like your model to kind of be sort of telling you something about the data, right? It should be intrinsic to the data. It shouldn't be a function of anything else, right? So, and regularization actually breaks this intrinsic property. Also, you can't regularize non-parametric models. What are you going to do there? So let's try to address these issues. So what do I mean by intrinsic, right? In graduate school, I did algebraic geometry, so you have to have a commutative diagram in every talk. Okay, but anyway, at least I'll try. So, right, so what do I mean by intrinsic? Well, the units shouldn't matter. It shouldn't matter whether you're quoting prices in dollars or cents or yen, or temperatures are in degrees or in Celsius, or rather Fahrenheit or Celsius, et cetera, right? The orientation of the data shouldn't matter, right? If you rotate, think of your data as kind of this cloud in this n-dimensional space. If you rotate it around and you try to construct your model, fit your model again, you should get the same result. It shouldn't really matter, right? So if you stretch it out, it shouldn't matter either. So ultimately, what I'm trying to say is that your model is giving you an observation, giving your features, it's telling you what to expect, right? And you pick this parameter p to best fit the data. Now, if you transform this data by a linear transformation and then try to find the p that gives you the best fit again, you should basically get the same model going around this way as you get straight across. Okay, that would mean that your model is invariant with respect to invertible linear transformations, which is a good thing, and that's because it means it's kind of more a function of the data and not of some other arbitrary decisions like the lambda that you picked in your regularization or your other hyperparameters, et cetera. Okay, so here's a theorem. Right, being a mathematician, I have to have a theorem in every talk, I think. There's a law about that. Yeah. Okay, so if there exists a function phi from the space of linear transformations on your feature space to surjective maps of your parameter space to itself, right? We'll say you're taking an automorphism A to phi sub A, has the property that your model with parameters p is equal to your model with phi of p composed with a for a given a, okay? That's basically saying that you can go around that loop and get the same model that we had in the commutative diagram. And this map doesn't just get you the same model, but it preserves your measure of accuracy. Then the model is invariant under linear automorphisms. As a corollary, we have that a model can be an arbitrary function of linear functionals on the factor space, and that model will be invariant to linear automorphisms if this error measure just depends on the responses. Okay, and the problem being with if I could go back and forth would be really cool with this thing, but in any case, the problem being that when you regularize, you don't have this property. This second property gets violated. Okay, so here's if you go through the math with all of these, you'll see that generalized linear regression, right, things like logistic regression, you're doing a regression, once you have some linear function of your factors, and you're applying some arbitrary function transformation to it, and you're fitting that. This is all invariant with respect to linear automorphisms. Bayesian regression generally is also invariant. You have a prior. If you change how you're expressing your factors, your prior has to be carried along with it. So you're also intrinsic. Maximum likelihood estimation in general is going to be intrinsic, as long as you have full coverage of the parameter space in a certain sense. ML models mostly would be also intrinsic if you don't use regularization. Once you use regularization, it all goes out the window. Okay, so what are we going to do? And this is something that was really bothering me. Maybe it wasn't bothering any of you, but they let me give the talk about it, so you're going to have to suffer. So anyway, well, I mean, you're all familiar with normalizing, right? Before you fit an ML model, you always normalize the data. So you might ask why. Well, this is one of the reasons, right? When you say normalize, typically people are subtracting the mean, dividing by the standard deviation, and it's required to make ML models work to some extent because regularization is not intrinsic. Okay, so if you think about it, if I ramp up the size of a factor, then the coefficient goes down and I have the same impact, which means it's not hurting my model as much in the regularization term, which means that just by changing the magnitudes of different factors, you can change how the regularization affects which model you choose. So, people get around that by normalizing. But, okay, so you've normalized, but your factors are not following a normal distribution. They have all different shapes. Some have fat tails, some don't. Some factors have a big impact. Some factors have a little impact. So you're kind of confusing all of this. You're not really taking any of that into account when you just normalize. Not to mention the fact that it depends on your training set. How are you normalizing? You're dividing by the mean and the variance of your training data, right? So you have a different training set. You're subtracting off a different mean and dividing by a different standard deviation, and you're getting slightly different results. Of course, and then there's the correlation between factors. I mentioned the parameter importance. And it's kind of incoherent if you think about it, because you have this norm that you're taking on the response, which has certain units. And then you're adding to it the norm of this vector of the coefficients, which are in all the different units essentially from the factor space. So it doesn't even make sense from a physics point of view that you're adding things that are in completely different units. It just kind of doesn't make sense. And it's still not clear, after doing normalization that you're really getting anything that's really intrinsic to the data itself and not just kind of some sort of arbitrary thing that seems to fit on your data sets, whether you're, regardless of what your test set is. Okay, so I'm going to propose a different way of looking at regularization, which I call functional regularization, and there's a paper that I wrote about it. And what we're going to do is we're going to try to regularize in function space instead of in parameter space, right? If you think about it from a computer science point of view, you're kind of destroying your what's the word for it? When you're using the parameters from your model, you're kind of going inside the model, you're ruining your abstraction, right? You should see kind of, even from just a general structure perspective, you really shouldn't do that. So what are we going to do? Let's go for it. Okay, functional regularization. Well, if you think about it, in some sense, what are you doing when you're trying to regularize? You're essentially trying to push the model somewhere, right? So think about the relationship between regularization and Bayesian estimation. Bayesian estimation is essentially also putting a regularization term into the estimate of the model accuracy. So what are you doing when you're doing Bayesian estimation? You're pushing the model towards your prior, right? You're not just picking the best out of the set of models that fits, you're also kind of penalizing it for being far away from your prior. Okay, so that's what we're going to try to do. So essentially what we're going to do is, instead of using this standard kind of regularization term, lambda times the length of your parameter vector, L2 length squared, we're going to say we should instead really be doing penalizing, no, that's right, yeah. Penalizing by the distance that your function is away from some reference function. Right, if you think about what this happens, if you think about what f is doing here for a given parameter, and that should be probably an f sub p there, but you have 0 penalty if your vector's all 0, and presumably if your parameters are all 0, your model is producing a 0 response for everything. So you're pushing it towards the 0 model. So here, you could just also make f0 identically 0, and you'd just be penalizing essentially by the norm of f, which if f is a linear function would be the sum of the squares of the coefficients, right? But it's a lot more flexible if you think about it, because we can put a different f there. We can say, well, no, I don't want to normalize by pushing everything to 0. I want to normalize by pushing everything to the mean. I want to normalize by pushing everything to some other function that I got from somewhere else that might work better or might have make certain sense. So how do we do this? Well, we picked some new points, right? Think about, we're going to have to basically, we want to compute this, f minus some reference function, the norm squared, so the integral of the difference squared. Okay, how are you going to do that? Well, you're going to discretize, right? How do you compute an integral? You pick a bunch of points and you multiply and add. So we pick a bunch of points and we multiply and add. And now think about this, right? So now, this is what we want to calculate, how bad the model is. And we've got the first term, the sum of the squares of the difference between the model prediction and the actual, plus this lambda, plus the sum of the squares of the model versus the reference model, times whatever your density you're using here, the derivative, right? So let's just put all this together. And really all you're doing is the sum over all the full data set of these weights associated with your observations times the sum of the squares of the differences. Which means that you can do this function, what I'm calling functional regularization, just by doing ordinary regression with weights. Okay, and then you just adjust your weights if you want more regularization, less regularization, or pick different data points for that matter, or pick a different reference function. So you have a lot more flexibility now. And what's nice is you can actually see exactly what's happening because you have your reference function and you're pushing everything towards it. So here's an example I worked up. It's like a bad example, but I think it'll illustrate. So I generated a cubic, and I made the features x squared, and x cubed. Right? You have all these data points, this cloud of data points, because I'm generating it with, I have some cubic behind the scenes plus noise, which is like with a sigma of 20. Okay, so a lot of noise. Well, because the value, it's cubic, so the values are going insane, right? Negative 400 to 400. And the red points are what I'm going to train on. You notice I really don't have much over here. It's going to get messed up. I'm going to use a really crappy model for this. Gradient boost. Okay, so I'm going to show you about how you're going to do what happens when you try to do functional regression using gradient boost, which is essentially a random forest type algorithm. You think about what it does. It produces a piecewise constant function over the full space and has all sorts of problems because of that, but we're not going to get into that now. Anyway, so, right, different learning rates, different number of estimators. You can see what happens. It's kind of like zigzagging around because you really don't have enough data points for this. And as you try to learn more and more, it just gets kind of worse and worse. Right, jumping all over the place trying to hit every data point because it can, because it's a tree and you're using real numbers. So this is where what I added to the data set was the same values in the original data set, but with the y value being the mean instead of the actual value. So I'm going to pull to the mean. And what you see, I hope, is that it kind of flattens out the noise. Okay, it's also pulling away from, it's kind of pulling it away from here, from the actual data, but you know, that's kind of to be expected because you're regularizing. You're not going to be hitting the data so well. But similarly, you can also pull it to linear regression, right? You see these extra dots here, those are the linear regression points that I threw in as additional points. And now it's kind of following, it's kind of smoothing and sort of pushing it towards linear regression instead of just whatever the gradient boost decides to pick. Okay, so basically, you know, from my perspective, you want the model to kind of be intrinsic to the data, right? You're trying to do a model for the motions of the planets, and you don't want something like epicycles. You want something like Copernicus, right? Makes more sense, simpler, et cetera, right? So your model really should depend on the data, not on the units being used, not on the embedding of the data in general into the space in which you're working. Right? Classic models like generalized linear regression, robust statistics, MLE models, Bayesian regression all do this. ML models generally don't because of regression, or rather regularization. So you don't really know when you're done if the model is really reflecting the data or is an artifact of how the data is expressed because the regularization is affected by that. So if you use what I'm calling functional regularization, you can regularize more intrinsically. You don't lose your invariants. You can do it with existing software, and you can use it to regularize non-parametric models as well. And then you can pick the number of points. You can decide where you're going to want to put them. If you have problems with your model extrapolating outside of your data set, you can force it to go towards that data set by adding points out there with whose values are your reference model. Like I've seen this technique done kind of in an ad hoc fashion for option pricing, where they know in the limits of the underlying that the option price has to go to some limit, so they put that limit out there and they kind of paste to it in an ad hoc fashion, but you can just kind of optimize for it if you just throw it in your data using functional regularization. Some references. Any questions?
All right, thank you so much, Dr. Stein. Much appreciated.